Welcome to the second lunch debate of WNE 2018. This one is about advanced reactors, generation 4 and beyond. Just a couple of words for the unfolding of the session. We have here la crème de la crème of the advanced reactor Gen 4 and beyond technologies. The names appear in front of the podiums. They will be answering 5 questions, video recorded with 5 experts. Each of them has about 2 minutes and 30 seconds to answer, so they will be very focused. The idea is that you will not get the answers to all your questions. The idea is that if you have more questions, you go and see them afterwards, and you continue discussion. You may even contact them at their booth or later on at their premises, and that in the end it ends up with a project. So I'm not going to talk much longer. You will have the opportunity to eat. They will not, me too. But then after the lunch debate, we are all going to move to the workshop number 2. There is a lounge. Then the speakers and myself will have something to eat, but you can then ask questions and interact with the speakers, okay? Well, so it's time for the first question, which is by Mr. Parmar from the Indian Embassy.
Hello, and good afternoon, everyone. I very much appreciate the technology development with regard to the advanced reactor, the generation 4 and beyond. I, however, want to know something about the generation 4 and the advanced reactors. What is the main technical breakthrough behind it? And does it aim only at the production of electricity or some other applications too? And what are the main advantages of the same with regard to the existing reactor technology? Thank you.
We shall start with Mr. Gauché, and we move from left to right.
So, good afternoon, ladies and gentlemen. So, among the different concepts of fourth generation reactors, the CEA is working in particular on sodium-cooled fast neutron reactor technology. France has gathered a lot of experience in this technology, but the goal today is to bring it up to fourth generation criteria. The requirements are to move forward with the most modern standards in terms of safety, to improve the economic competitiveness, to strengthen the proliferation resistance and the physical protection of such machines, and to optimize the fuel cycle with regard to nuclear materials and the waste management. At the request of the French government, the CEA has been conducted R&D and design studies for a reactor that is called Astrid. Breakthroughs have been made in the design of the core with intrinsic safety features or in the design of heat exchangers and energy conversion systems. We have made also improvements in the simplification of components and of the systems, and also with regard to the inspection of the structures. As you know, the liquid sodium is opaque, and we need to look to be able to see through it with the help of ultrasonic technologies. Also, the requirements resulting from the feedback of experience of the Fukushima accident have been taken into account. In particular, the guarantee of a safe state in case of loss of power supplies for several days. More broadly, the safety improvements have been obtained on the prevention of core melting accidents and the resistance to external attacks like earthquakes, floods, or plane crashes. Fast neutron reactors have many advantages. In particular, they operate from depleted uranium fluid, plutonium from the reprocessing of spent fuel. There is a large amount of depleted uranium that is already available in some countries like France, and this quantity will be enough to provide electricity in a fleet of fast neutron reactors for for several hundreds or even thousands of years. And in addition, there is also the ability, because of the high temperature at the core outlet temperature to open the door not only to electrical applications but also to non-electrical applications like heat production. Thank you very much.
Mr. Bigot, you're next.
Yes, as you know, the project I am in charge is ITER. It's quite innovative technology. The main technical breakthrough is to demonstrate that you could produce electricity through the heat production in the first step with fusion of hydrogen atom under magnetic confinement. So the main advantage is clearly you have enough raw material for millions of years because it's very highly distributed. Just to let you know, in order to have enough raw material for producing 1,000 megawatt for a year is only 350 kilograms of hydrogen, quite very small quantity. So it's a long-term capability with the raw material we have. It is intrinsically safe because at a given time you have a very few grams, okay, less than, for example, 2 grams of hydrogen within the reactors. And if any parameter are not online with the nominal specification, the reaction stops. You could lose the cooling water system, okay? No difficulty on that matter. And the third big advantage is that you release only helium, which is, as you know, a non-active chemical, neither radioactive material. So it is with this big advantage that 7 large members are working together to develop this technology. And the main purpose is to produce electricity, a large amount of electricity, massive quantity of electricity in a continuous, changing, even predictable way. So I really believe it is a breakthrough, and if we succeed, it could provide a very long-term capability of energy supply for the world in complement of the renewable energy with different features. As you know, they are intermittent and they are diffuse, and here we are massive and we are continuous and predictable. So it is why all these partners accept to invest quite a large amount of money in order to be able to demonstrate this feasibility.
And it's a fabulous project.
On time.
Rory, you're next.
Thank you very much, Gerard. Hello, good morning all. So we, like a couple of others here, are a molten salt reactor. The big differentiator with us is that we have molten salt fuel contained in tubes, allows us to control the chemistry a little better and manage corrosion. Another one is that we take spent nuclear fuel, spent oxide fuel generally from any of the PWR heavy water reactors, and we don't need to reprocess it to use it as our fuel. Essentially, we just convert it from one form straight to another. We don't need to do the heavy separations that you'd normally need to use. So we actually, for our business model, we encourage the expansion of the PWR fleet. We really want it to grow because that waste is great. What all of that leads to, though, is unparalleled safety, and that's the same for virtually all molten salt reactors. We have no emergency planning zone requirements, and essentially infinite walkaway safety. It's way beyond the 7 days the advanced reactors of today, the advanced water reactors today are seeing. What that safety leads to is simplicity in the design. Simplicity in the design leads to ease of construction and, most importantly, low cost. And that's really all that we're about, is low cost. We expect our capital cost to be comparable with coal. If we don't get that, it's not even worth trying. The low cost leads us to the electricity market, so that's really what we're focusing on, the big gigawatt scale electricity market. In the future, there are other opportunities in the industry, but today we're focusing on electricity and using nuclear as a peaking plant to be able to complement with renewables as we go in the future.
Thank you. Mr. Pershukov.
Okay. Hello. Bon appetit to everybody. Thank you that you're coming. And I try to answer very short for each question. Generation 4. Now the generation 4 considered the sixth system, but in Russia we consider just a few. Most of all is the fast reactors, sodium, lead, and the lead bismuth coolants. And for thermal reactors, we can see the improving of our WNE where and the thermal reactors is industrial scale light water reactors for regulation of spectrum and supercritical. And last 30 years, we tried to do something in R&D area for molten salt reactors. Just 30 years. But we are not ready to start industrial scale, develop the technology. We really understand some problems, mostly not for reactors and for fuel of reactors, but mostly for including this type of reactors in the closed nuclear fuel cycle. For second question, what's the general goal of our generation 4 reactors and what we are doing? Of course, it's not only reactors, but mostly it's closed nuclear fuel cycle. What is not closed nuclear fuel cycle? It's we're free from the uranium reserves, we have a new fuel, and we need to create inherent safety. Inherent safety reactors we can arrange and can design only on the base of fast breeder. And fast breeder, or fast reactors, we consider two directions. First direction is lead coolant. And lead coolant, we consider the special project with fabrication, reprocessing, and fast reactor together. It's one place. It's a very wonderful decision. And second is the sodium fast reactors. We complete all test and demo and demonstration of this technology on scale 800 megawatt, and now we start the design of industrial scale. And so general goal of our technology is closed nuclear cycle, of course, with production of electricity. Thank you.
Okay. Troels, you're next.
Yes, like a lot of other people here, we develop a molten salt reactor, and our take on it is to develop the tech, very tech focused. And what we see is that if we develop the tech, we gain risk, and when we gain risk, it takes more time. When it takes more time, we need to not aim for first to market, but as one of the second to market. This means that we need to do innovations that makes our reactor more efficient or better. And our key tech development is actually a scale down of the molten salt technology. Molten salt reactors are good in the normal small modular reactor class, the 300 megawatt, but we're trying to go much smaller. I think the molten salt reactor should be explained more in details. We all have the same value points, and I will warm up for you there. Molten salt reactors are very different from other reactor technologies in that the physics is in charge. This means that you actually make all the complicated engineering safety systems redundant. If you can do that, then you have massive savings, and you make nuclear cheaper. And you also, when you scale it down and have these simpler systems, don't need massive pressure vessels. You actually are able to deploy these in another fashion. You don't need to educate a large workforce on site and then build a power plant. You can actually educate a workforce on a shipyard-like facility and mass produce these modules, put them up in the sites. So it's another take on nuclear, and it's a very new form of deploying nuclear, which the industry is not used to. So we actually mainly operate outside the nuclear industry because it's a little bit conservative, and we want to be flexible. Yeah, I think I will.
Thank you, Troels. Okay. Simon, please.
I'm on. Well, thank you very much. It's a pleasure to be here today and contribute to this discussion. So, as you've probably understood already, we are developing also a molten salt reactor. Our design has its roots very much in the work that has been conducted over many decades at Oak Ridge National Lab in the United States. So, this is a molten salt reactor that is a fluoride chemistry. It's a thermal spectrum reactor, which was the reactor that was demonstrated at Oak Ridge. The key innovation, though, for us is the use of a sealed and replaceable reactor vessel, and that is important. because many of the components for use in a molten salt reactor suffer a limited material lifetime when you're seeking to operate those materials and components in a molten salt reactor system. Those technical challenges are removed if you simply seek to replace the reactor vessel every 7 years, swap it out. That's what we're doing. But from a broad perspective, the great innovation here, we believe, in using a molten salt fuel and coolant is, as mentioned already, is that you avoid the complexities, the considerable engineering complexities of using highly pressurized water as your coolant. Our system operates at 1 atmosphere, and you can achieve your engineering case, your case for nuclear excellence, which is the commercial and regulatory objective, can be achieved at much, much lower cost. And that is the commercial essence and driver behind what we're doing. The other great advantage is versatility. This is a high-temperature reactor system. It's not the only one in Gen 4 space. There are others, and a couple have been mentioned already. So you have the opportunity of a reactor system which can create heat, can operate a power cycle far more efficiently from a thermodynamic perspective, can deliver heat to industry to displace natural gas and heating oil in many industrial applications. And it also is a reactor system. Our reactor system, called the Integral Molten Salt Reactor, can load follow. So this is a feature of a power plant these days that's increasingly prized by utilities as we see greater penetration of wind and solar generation on grids. So this is a system that can back up wind and solar, strongly back up wind and solar, and avoid the need for additional hydro and possibly a storage breakthrough. Thank you.
Thank you. Jeff, you are the last one to answer this first question.
Thank you very much, and thank you all for being here. X Energy's XE100 is a high-temperature gas reactor, Pebble-Bed fuel. This technology has actually been around for a very long time. It was invented at Oak Ridge, Tennessee in the USA in 1944, and thanks to the Germans, they've actually operated this technology for around 20 years. I think the major breakthrough, if you will, in this technology actually resides in the fuel itself. The fuel sphere, it's the size of a billiard ball, actually is called tristructural isotropic fuel, we so-called TRISO fuel. In fact, one of these pebbles, as we call it, has 7 grams of 15.5, in our case, low-level uranium, low-enriched uranium, and it actually equals 2.6 metric tons of coal. I mean, it's really amazing. The design that we have has low power density, the core geometry, and also the pebble material, largely graphite, meltdown proof. So it allows walk-away safety, minimum operator intervention in case something goes wrong. You can build a safety case around that pebble itself. That's just truly remarkable and can be and is revolutionary as far as we're concerned. I think some advantages that we have also would be this is really a small, versatile, and simple system, which is beautiful, actually. 20 meters high, 4.88 meters in diameter. Facility can fit on 0.72 square kilometers, which is very small. Lends itself to distributed power, cogeneration applications, meaning electricity, process heat, and also does not need water for moderation.
Super. Thank you very much. It's time for question number 2. This question is by Jean-Jacques Gautreau, former chairman of WNE.
The third generation of nuclear reactors represent most of the nuclear means of electrical production and has a level of maturity and safety very satisfactory. Tomorrow, advanced nuclear reactors will have to cope with more flexible production of electricity and has to integrate load following and various size reactors, development of new products and services such as cogeneration and hydrogen production, not to mention the coexistence with the renewables. Tomorrow, Gen 4, associated to closed fuel cycle, could possibly emerge, in particular to take care of the long-term sustainability of final waste. And ITER showcases international cooperation in mastering fusion for the long term. Here are my questions. How advanced is your design today? What is the estimated time to market? And last, what do you need to move forward?
Mr. Bigot, this time you are the first to answer.
Okay, thank you very much for this question. How advanced is your design? Our design is now complete, I would say, because we have over 50% construction complete now. We have quite a few points to finalize, mainly the recycling plants of the fuel, but it is not a blocking event, and we are on time. As you know, we expect to be ready by 2025 for first plasma and full fusion power 10 years later by 2035. What is the time estimated to market? Clearly, it's a little bit premature to just make an announcement on the market, since we are just developing the technologies. But our expectation that the technology will be ready if we are complying our plan by the mid of the second part of this century for a large deployment after we move from the research development to the first prototype, and after that, the industrial deployment. So it will be around 2065, 2075 in the best of my estimate. The breakthrough is so large that we could not expect to move for faster. And what do we need to move forward? It's very clear. We need continuous support of the 7 ITER members. Clearly, we need also the full support of all the suppliers. There is a lot of innovation with the superconducting coil, with the heat transfer, with the vacuum, with the cryogenics. All this requires a lot of innovation, and for the time being, we are pleased to say that some of the best world companies in this different field are fully involved and want to demonstrate their capacity to complete or design, construction, and starting operation. So thank you for your attention.
Thank you. Rory?
Thank you, Gerard. The design question is, we always find that really difficult, how we specify exactly where we are with the design. But I suppose to summarize, I'd say we're beyond concept design in a nuclear sense. We were a paper reactor design. Now we're a lot of paper reactor design. To put it in perspective, we have enough information to be able to produce a preliminary outline safety case, and we're taking that to the Canadian regulator at the moment as part of their vendor design review. So it's not enough for a full safety case for a license to construct. That would be about 2 to 3 years away, but well into engineering design phase. In terms of timelines, we hear a lot that Gen 4 reactors are going to be deployed not before 2050. So because of this consensus, what we thought we'd do is commission a study with ourselves and our advisory board, and we used AMEC Foster Wheeler, looking at our timeline, all the risks, all the construction schedules, licensing issues, both in the UK and Canada, to see what the actual realistic timeline is. The conclusion of that it is viable to have a commercial demonstration reactor online in under 10 years. And that was peer-reviewed by Ontario Power Generation Utility and Canadian Nuclear Labs. From the business side, Deloitte were heavily involved in that as well. So there is credibility there. In terms of our needs, we're a startup. We're always looking for cash, so finance is the biggest need. One of the issues we're finding with finance is when you say nuclear, people are afraid. You lose 90% of investors immediately, and that's linked to the policy risk. So governments really need to get on board promoting this. And actually, we're really happy to announce today that the UK government has released their nuclear sector deal as part of their industrial strategy. there's been a few industrial strategy announcements over the last year, and we are selected as one of the advanced modular reactors to move forward with their program. So that's looking at doing a technical evaluation of our design. We're producing safety case for the regulator, and also a submission to take part in a £40 million funding pot at the end of this year. So we're really looking forward to that. It's great to see the UK government actually moving on advanced nuclear.
Thank you, Rory. Mr. Pershukov, how advanced?
Okay. Regarding the advance for is our design. The last 50 years, we are not stopped the program for fast neutron reactors. During the 50 years, we start up and decommission a few type of reactors. Fast reactor 5 megawatts, 5 reactors 10 megawatts, fast reactors on the with sodium 350 megawatts. Now they operate sodium fast reactor 600 megawatts, and now we put to operate 800 megawatts. What does mean where we are? Now we are ready for start the construction of commercial scale construction of the sodium fast reactor BN 1200s. It's a fast reactor. Regarding the fuel, we construct the special plant for MOX fuel, and now we complete our program for nitrate mixed plutonium uranium fuel, and working for other type of fuel like the all members of nuclear society. And so we are ready to input the market our fast reactors, and we start that discussion, and we are ready proposed for market the fuel for fast reactors. And the next 10 years, we're sure that we will be ready to propose for market not only fast reactor, and the whole philosophy and whole elements of the closed nuclear fuel cycle: fabrication, reprocessing, and fast reactors. It's our situation. Thank you.
Okay, Troels, you're next.
Yes. So first thing I will do is answer or misunderstand the question deliberately and say our reactor is actually not advanced. It's simple. That is the whole point. But then I will admit that we are on a conceptual design stage. We do have hands-on in the lab, and then it is progressing, but we have a long time to market. We are hoping to start or to go into construction in the mid-20s, but this is also, it might be a little bit ambitious, but that's our aim, and of course that requires a lot of elements to fall into place. So what do we need to move forward? I mean, we need to work, and we need more hands. It would be really nice if, I think, if we could leave Europe at some point, because Europe is it's a very conservative place, and it's very hard to get grasp of funding, and it's actually slowing you down. So we will hopefully open up an office somewhere where we can work faster soon. But yeah.
Okay. Simon?
Thank you very much. So in terms of how advanced our design is, we have an industrial design for a first commercial power plant. It's not a prototype. That, as I mentioned before, that system is based around, the heart of that system is based around much of the work undertaken at Oak Ridge National Lab. We are been in engineering the past 3 years, and that engineering program has supported a first regulatory submission to the Canadian Nuclear Safety Commission. So this has allowed us to achieve, I think, a very important commercial milestone, that we can point to the licensing viability of our system. And that is a very important development. We will shortly be starting phase 2 of the vendor design review process, and we'll be aiming to finish it within 2 years. In terms of estimated time to market, we're looking to commission first plant with first customer in the late 2020s. To achieve that, we will have to convince our first customer of several aspects, certain key risks associated with the design. The first one is licensing risk, licensability. We believe we'll address that by completing the vendor design review process with the Canadian Nuclear Safety Commission. We will have engineering to support constructability risk, demonstrating constructability and operability as well. Our system uses standard assay under 5% low enriched uranium. We're a generation 4 system, yes, but we use standard nuclear fuel, and I think that's very important when demonstrating operability to a customer of your design. And we're seeking to secure first customer based on discharging those risks, assuring the customer of those risks within 3 years. What do we need to move forward? We need to have continued support from government policy. This is the nuclear industry can't operate in a vacuum. It has to operate in partnership, in regulatory partnership, and in partnership with industrial policy. We'll need a supportive industrial policy environment in our core markets. We also will need the support of our supply chain. We recognise that the nuclear industry, after 50 years, has a mature and very sophisticated supply chain, and many of those capabilities we can use rather than attempting to do it internally. The third, probably the final point, is reaching out to our customer group. And we are in the process of doing that today. I should leave it there. Thank you.
Okay, thanks. As mentioned previously, this is proven technology. So our real challenge and work is really in economics and also in licensing. Having said all that, we are somewhere between conceptual design and detailed design for the reactor. You should also note that we also have a fuel manufacturing effort at X Energy. We're calling it TRISO X. And TRISO X should be online somewhere in 2019. So it's near term. The actual purpose of that organization or the mission there would be to supply TRISO fuel into the advanced reactor market. So in terms of our reactor, we're looking at first of a kind, similar to most here in the late 20s. What do we need to move forward? Our CEO reminds everyone all the time in the company that this is not a hobby or a science project. So what we really need is a first-of-a-kind customer. So what I really need to do and what the team needs to do is to close that first-of-a-kind customer. We have an MOU with Jordan at this point in time. We're striving to try to make good on that. Not only with Jordan, but in other areas as well in the United States, etc. I guess the second biggest rock that we have to move in terms of our need would be funding, which is not a surprise. So in terms of TRISO X, there's funding requirements, and also in terms of the reactor, there's also funding requirements. I think there's another question. We'll get to that later.
Thank you, Jeff. Monsieur Gauché, you're the last to answer this question.
Thank you. Actually, sodium-cooled fast neutron reactors are already operated and being built in several parts of the world. So I think the question is, what kind of safety options do we put into the design, and how far are we with regard to the competitiveness? So with regard to the Astrid reactor project, we are I think we are quite advanced in a detailed design, and we have submitted to the French Safety Authority a safety orientation file that was already examined several years ago. There is tremendous feedback of experience of such technology, more than 400 reactor years in the world. And as you know, there is also this possibility of having a non-pressurized primary circuit and also passive cooling systems that are connected directly to the atmosphere as a heat sink. So this provides very intrinsic cooling features that are possible. So I want to advertise a little bit for the other countries. You have 3 reactors of this type that are operating in Russia. 2 of them are in commercial operation, BN 600, BN 800, with different levels of safety features, and BN 1200 is a very interesting design as well, and we have also tried to inspire ourselves with the Astrid design, looking at what our Russian colleagues are doing. But there is also an acceleration in China. China operates a small reactor, but they poured, and it is not very well known, the first concrete of their 600 electrical megawatt sodium-cooled fast neutron reactor between Christmas and New Year this year. And India is also in the process of commissioning a 500 megawatt reactor. So to move forward, of course, we need political decisions, we need public acceptance, we need financial support. I think like everybody here around the table, even if the size of our project are not exactly the same, we need finance. And but we need also, I think, more use of numerical simulation and also dedicated experimental facilities to provide for the right qualification of the technical options that we will put into our designs. Thank you very much.
Thank you. We move to question number 3. This question is by John Lafad from Chief Scientific Advisor, BEA.
The future for civil nuclear power has to be as a competitor in commercial energy markets. At present, civil nuclear is being outcompeted by the alternative sources of supply. So my question for you is, can the civil nuclear industry develop a product that is truly suitable to be sold to an international marketplace? If you can do that, how can you compete with electricity costs that are likely to be regularly below 50 euros per megawatt hour in the coming decades? What do you need to change in the environment to enable the industry to do that competitively? If you can answer those, I'd be very happy.
So make Mr. Lafad happy, Rory. You start.
We'll do our best. So in terms of the industry being able to do this, of course, we're going to say absolutely. The attributes of the technology that we talked about earlier really change the potential opportunity for investors. So our long-term aim and even near-term aim is for the industry to do this without government subsidy. And to be honest, if nuclear is always going to need government subsidy to compete, it's not even compete, it's not even worth trying. So that's one reason we think industry will be able to do it. We don't need government in the long term. Because the economics are there, the price of 50 euro per megawatt hour was mentioned as a future price. In the UK today, the wholesale rate is around 45 euro, I believe, but we're talking about 35 euro a megawatt hour. Those estimates are done independently by Atkins, so they're not even ours. We have a lot of conservatism built into them. And if we're not going to get that high, as I said, we're really not going to try. Another advantage way of getting industry involved for the international market is countries always want local supply chain. They want local involvement. The simplicity of some of these advanced designs, and I know ours as an example, enables local manufacturing, enables a local supply chain to have a greater share of compared to what they would have from something like a pressurized water reactor, where you'd have these huge components that need very specialist skills. That's not the case. So this is more suitable for newer nations that want more local involvement. So now nuclear is very policy linked. As I mentioned earlier, you say the word nuclear to an investor and they're gone. They've hung up the phone already. So there is need for some government involvement now in the early stages because nuclear is so policy linked. The UK, for example, doesn't allow us to access the regulator until something like this happens with the sector deal, industrial strategy that I mentioned earlier. One of the reasons we've gone to Canada is that we can talk to the regulator there. So governments need to unlock the doors. They need to allow us access to regulators. Essentially, they need to get out of the way eventually. That needs to be the end goal, and the market needs to be able to compete. We need to work like a conventional market, and there needs to be competition to get those low costs.
Good message for our political support. Mr. Pershukov.
Okay. And really we agree that today the levelized cost of electricity for entering reactor lifetime exceed $50 per megawatt hour. But what the component of this price? And this component of the price may be fuel, not a lot, but fuel. Second, safety system. And third, maybe a new type of technology. New type. I understand it. For light water reactors, we have a lot of experience, but it's only 70 years this industries exist, and so it's a new type of technology if compared with gas turbine, with coal, and other sources. How to reduce this cost? For our understanding, we need to construct closed nuclear fuel cycle. In this, we have on the feedstock just uranium-280, and we have the reserves for this type of uranium in the world for more than 1,000 years. And the fuel cost close with zero. And second is the reducing cost for safety. It's not reduce safety, reducing cost for safety is new type of design and inherent safety technology, what we are doing with our design. In this case, and so are the opinion of the society of people, we demonstrate that inherent safety and low volume of the spent fuel, zero price of the feedstock. I think we will have good relations to this type of technology. It also help us to make some more design, more detailed design with reducing the cost without very huge resource on safety. And so, for my understanding, closed fuel nuclear cycle with new type of reactors help nuclear society to reduce cost and be competitive with a new type of renewable source of energy. Thank you.
Troels, please.
Yes, so the answer to the first question is simply no. I don't think so in the Western world. I think it's pretty clear. I think the civilian nuclear industry haven't done this. They have failed to deliver. We don't have nuclear reactors everywhere. We were told that it would be too cheap to meter, and now it's too expensive to build. So quite apparently the civilian nuclear industry cannot really do this. But okay, that might change, and I think this is what we are trying to do here. And I think with a lot of other people here, we're trying to change that. And that's not easy, but it may be done. And I think one thing that we have realized is that we need to, the customer is, the developers often see the customers as EDF or somebody, but their customer is usually the government, and their customer is actually the people. So you need to make a nuclear power plant which is not just sold as being safe. It needs to provide something for people. And what people want now is something which is green, something which is not polluting. And if I look around at this exhibition, I see no one selling that their technology is sustainable. They're all selling that they can decommission it, and that that it's safe. And it's just the wrong thing we are selling. And that's going to be really hard to implement into the civilian nuclear industry. So I somehow feel that the civilian nuclear industry is in the way of nuclear power being deployed. It's a little bit controversial. And I will also say that this only applies in the Western world, being the States, Canada, and Europe. It doesn't apply if you look in the East. So that was my small provocation here.
Okay, Simon?
Yes, I think some pretty hard questions have been raised actually by John in this session, and from my perspective, I think the principal challenge for nuclear is that it has lost its relationship with private capital. The nuclear industry now relies on a government seller and a government buyer, and that demonstrates to me a very, very poor state of health. If the nuclear industry is to sell product into existing and new market, it must re-establish a relationship with private capital, and that can only be re-established by significantly reducing the price of the product. And to achieve that, you need to innovate. The $50, €50, $60 a megawatt hour number, I don't know the basis of that, but there is at the heart, I think, a general principle here. Innovation is deflationary in any industry, and in the global market for industrial heat and power, the industrial competitors to the nuclear industry are innovating. The wind and solar guys are innovating. The fossil fuel guys are innovating, and they achieved a big step change in innovation in the last 10 years with a tremendous commercial success with hydraulic fracturing. The nuclear industry has to innovate, and it has to innovate by having a product which maintains a cost-competitive position in a competitive global market. It cannot continue to exist by acting as a government seller and seeking a government buyer, because it will not, in that construction, nuclear cannot realize its true inheritance in the global economy, and that is, to echo the point made a few moments ago, and that is, as a nuclear technology that can scale quickly to provide the global economy with a clean, zero emissions, clean, sustainable industrial energy source. It must, if it's achieved that, it must re-establish a relationship with private capital. And just comment on our system, we think we can do that because with our innovation, and we have committed to be innovative, to be truly innovative, we have a power plant which we believe can deliver at $50 a megawatt hour, so maybe €40 a megawatt hour, and that's what we believe our technology is capable of. If you can deliver on that, you will establish a relationship with private capital. Thank you.
Thank you. Jeff?
Yeah, I'm more optimistic. I think there's a fresh wind blowing, and I believe that we need an industry to make this happen. And we have an industry here that's developing. There's a think tank group in the U.S. called Third Way. They say there's 30 reactor companies out there. Maybe not all of them will survive in the end, but you know what an industry does is it basically attracts capital, it attracts talent, it attracts supply chain. These things will eventually, as Simon says, I agree, keep innovation going, etc. All of these companies are pretty much motivated by clean energy, by profits. I think it's terribly exciting, and I believe we can get there. In terms of the question about the 50-year-olds, I mean, basically, we're in the States at least, we're talking about natural gas, and I think in the short term, we really need to use our attributes not to compete with natural gas head-on. So we're finding markets where we don't have to do that. Namely, there are remote areas that are using diesel now that we can surpass from an economic point of view. There's a whole clean energy aspect of what we're doing. Renewables, for example, in X Energy's case, we can couple our XE100 with a solar facility because we're able to load follow, meaning we can go from 100% power down to 40%. We can do that 5% per minute. So all these things, I think the last part of the equation, at least in the States, would be public perception of nuclear. Most people think nuclear is nuclear. They don't discriminate between the large nuclear and what we're trying to achieve here with our advanced reactor designs. And, that's problematic, really, because most people don't think clean energy when they think about nuclear. So maybe public policy can help us in terms of valuing this clean energy, as at least in the States they've done with solar.
Thank you. Monsieur Gauché, please.
Thank you very much. So I think the three questions are very difficult to answer for state-owned research body working with state-owned big companies. However, I think that we need several conditions for innovative nuclear systems to be competitive in the future. Some are internal to the nuclear industry, like innovation and so on, making our reactors cheaper, with more performance of the fuel and so on and so on. But there are other factors that have to do with, from my point of view, energy policy makers. And I will list at least three of them. First of all, I don't think that the current electricity markets, so in some places of the world, and the way the different players get remunerated can be sustained very long, because there are too many situations of malfunctioning of those markets. I don't want to be too long on that, but my point is that it does not apply only to nuclear energy. It applies also to other conventional energy sources, and even in some cases to renewables, or they will see that very soon. So I think there is a need to fix these markets so that they can function properly, and then let the key players be able to play with the same rules. And I think that there are already attempts to do so in some parts of the US, for instance, for grid stability reasons, or even for climate reasons. The second factor, from my point of view, is that one of the big advantages of nuclear energy is this low carbon content. And it means that real carbon signals must be given to the markets. And this is not necessarily the case today. And for me, this is a condition for the deployment of future nuclear innovative systems. And a failure of doing so might result in further delaying the fight against climate change. And the third external condition, from my point of view, is the development of international licensing standards. There are many initiatives aiming at harmonizing safety requirements, that's for sure. I think these initiatives should be accelerated. No country will be able to have a regulator that is knowledgeable of all different technologies at the same time. So it means that some concepts, for instance, like small modular reactors, they pretty much rely, from my point of view, on the fact that there is a possibility in the future to have international licensing procedure, committing ones. Thank you very much.
You're right, that was one of the topics yesterday at the SMR lunch debate. Monsieur Bigot, please.
Yes, thank you very much again. Clearly, as you know, the ITER project is on a large international base. The big breakthrough is that we decide together, before we launch the technology, what will be the new technologies. We have 35 countries behind the ITER project which have agreed that the best way to move forward is the design we are considering. So my understanding is now there is nearly 8.5 billion of order which has been passed by the industry. I know we request quite challenging specification and tolerance. Some of them have some difficulty to come up with, but my expectation is that the you say nuclear industry, for me is the industry. Okay, on magnetism, on cryogenics, on vacuum, they are really prepared to deliver what we expect in order to move with these technologies. And the international rules are already set. Big advantage with the difference coming from the previous fusion technology. Second, the questioners speak about 50 euro per megawatt hour. You know, I am very amazed that people could speak this way. It is not at all sustainable. Okay, electricity has a much higher value than that. So maybe it will be the double or something like this on a sustainable way. Even with the renewable, in competition, when you have the full cycle. The full cycle, you need a backup when you have renewable energy. You need to be decommissioned and all these things. So my expectation, even if it is too early now to say, but our goal is to be really competitive. We have a really competitive advantage, as I mentioned to you, this flexibility, coping with the need of the consumers, and also no release of waste, no difficulty like this. So our expectation in our work is to be really competitive. It's not just a dream for researchers. It's really to be able to supply energy on the long term, safely, and without any impact on environment and climate. So, do we need a change on the environment? It's maybe a cultural change. Let's stop to dream that there is just a single bullet and that just the windmill will provide the electricity for everybody. You need to have some diversity, complementary technologies, and I do believe that the fusion technologies is complementary of potentially the fission nuclear, even more with the renewable energy, and people has to be realistic. We need to find an alternate to the fossil fuel we are burning now. Everybody knows that the fossil fuels is just an interim storage of the solar energy, but the storage has been developed during millions of years, okay? And so now we need an alternate for millions of years, and I do believe that fusion could do it.
Thank you very much. It's now time for question number 4. It's going to be by Walter Hoos.
My question focuses on one of the most challenging issues relevant to every next-generation nuclear technology, how to pay for them. The sources of capital that can tolerate the kinds of risks involved in this sector may be large in scale, but certainly small in number. Public sector funds, governments, sovereign funds, private sector funds, private equity, family offices, wealthy elites, Bezos, Gates, etc. Occasionally a bank, maybe with a government guarantee, and public-private partnerships. So my question is, what is your strategy for obtaining financing?
Interesting question. Mr. Pershukov, you are first to answer.
Okay, thank you very much. Of course, certainly nuclear energy has its specific features, including the longer payback period. So, the project with liquid reactors require long-term financing, which can be provided by the limited number of investors, such as budget, financing or state guarantee or for bank debt, sovereign funds, and development institute. Maybe it's just unique situation for Russian Federation, maybe not. But now we start working for public company like Finavoima and our Turkish project. We arrange the shareholders financing, but also we use some connection with private equity funds and the private investors, like for small reactors, it's SVBR, it's the fast reactors. We now complete the design for lead bismuth reactors together with Mr. Deripaska. But mostly for Russian Federation, of course, we use the state guarantee as state financing. It's clear. And we try to use other source of financing, but it's not easy. Thank you.
Troels, you're on.
Yeah, so when we talk about financing, everyone talks about risk. And I think where we are focusing here in our company is definitely the tech. If we can develop the tech to a certain level, then it will just be a matter of how money you can earn. And then you will attract the big money. They may not come from the nuclear industry, as you say, the numbers of investors are limited there. However, outside the nuclear industry, there are more and more big investors. But of course, it's challenging to get there. And when you're an early stage company with a long time horizon and you don't even try to hide that you have an ultra high risk, then investors tend to walk away. But the potential is big here. So at this stage, we have attracted our financing by having vision and finding visionary investors with guts. And we are aiming for the moon. It might take a long time for us to get there, but I mean, mid-30s, we will buy Siemens or similar. So we're going big.
Nice ambition. Simon?
Yes, thank you. I think it's an important question. I would disagree on one point. I don't think this is a financial moon mission. So part of the Generation 4 opportunity is you can develop a Generation 4 system as a vendor for under $1 billion, and you can construct a Generation 4 power plant, these are our numbers, for under $1 billion. So yes, there is risk involved in both of those aspects of the project from a vendor perspective in developing the technology, and from a first customer perspective in buying and building the technology. But there's also tremendous opportunity. Generation 4 systems offer the opportunity for nuclear innovation to deliver on the key commercial objective, which is cost. And I think capital is sophisticated enough to appreciate both sides of that coin. The risk side, yes, there are risks. And the opportunity sides, yes, there is tremendous opportunity. And I think capital will appreciates that, increasingly appreciates that opportunity. In terms of sources of capital, we're being funded at the moment by private investors. We're being supported through grants from the Canadian government, and our US project is being supported by grants from the US government. And those grants are directed at the two important constituencies: to the developer in grants that help and assist with mitigating some of the risk of developing the project. And they're also directed at the vendor who is taking the risk, taking the burden of being first customer. No one wants to be it. But government policy in North America, there are home markets North America, is moving to support the first customer. And that is in the form of loan guarantees. Our US project has a $1 billion loan guarantee in progress with the Department of Energy, and recent legislation in the form of a production tax credit. That tax legislation in the United States has been amended to support 6 gigawatts of new nuclear capacity, which will include potentially the first Generation 4 power plant, potentially our power plant as well. So there are many industrial mechanisms that are policy mechanisms, policy tools that are being developed to mitigate the risk of development. And as you mitigate those risks, the equation for private capital becomes much more favorable.
Thank you. Jeff?
Okay, I think you eat the elephant one bite at a time. Basically, first of a kind, we need about $2 billion, if you will. Our CEO, Cam Gafarian, has spent his own money, up to $40 million as of this year, 2018. Let's call him an angel investor. We're looking for others. The other thing would be family offices, wealthy individuals who come together, such as Cam, maybe. The other one is very important, is public-private partnerships. So in our case, at least, we have been very successful working with the U.S. Department of Energy. We have a cooperative agreement for $53 million. And then we also have just been successful, another one, which is a $9 million award for 3 years, so $9 million for 1 year each. Okay. So I think with that, we're also going to be looking at the debt market through, we're working with Verdigris to look at a DOE loan program, which would, guarantee debt. Strategic partnerships, we are also working with, companies like Burns & McDonnell and some others who cost share with us. So anything that they do, they'll do it, free, or in essence, working with us on their own nickel. I think the other thing that we're exploring is how do we bring in a profit-generating subsidiary to X Energy so that we can at least look like we're earning, we can be earning some profits, some revenues and profits as we're marching toward our goal. I think as time gets closer to our deployment, we can start looking at the equity markets, but equity markets are actually very tough.
Thank you. Monsieur Gauché.
Yes, thank you. I think we are facing a clear challenge is how we can convince the different stakeholders, including the general population, of the benefit of these advanced nuclear technologies. in terms of their contribution to the fight against climate change, but also with regard to the services that they can render with the nuclear materials, nuclear waste, spent fuel, and also with regard to what they can do in decarbonizing other sectors of the economy and not focusing always only on electricity. And I think this should help also to set up maybe some new financing schemes that could be supported in part by public authorities that are in charge of the fight against climate change and also that are also in charge of energy independence. So with regard to the fast neutron reactor program in France, we have put in place since 2010 basically a kind of private-public financing scheme. There is, of course, a big investment from the French state via the so-called Programme on Investments for the Future. But what is less known is that we have also several, more than a dozen industrial partners. They contribute to the design studies, and some of them are represented in this room, and I thank them very much for that. And so they provide also a share of their contribution is based on their own funding. And this is, and we also try to develop an international collaboration that not as broad as ITER, but we try to have some efforts to put resources in common with some like-minded countries to develop our fast neutron reactor program together. And this is why we have a very quite big collaboration with Japan involving almost 100 engineers in Japan working on this project since 2014. Thank you very much.
Monsieur Bigot.
For ITER, we have two phases, indeed. For the present phase, which is the construction and operation of the facility, all stakeholders are already convinced of the advantage and benefit of the project. And so to keep them, okay, and to be sure that they go and trust on us is we have to keep with our schedule and our promised performance with these people. It's so important that we built trust in the capacity to deliver according to the plan. When I came in, we have revised completely the project, and I believe we have a challenging but credible schedule, and we have to keep on schedule. It's, for me, absolutely critical for that purpose. So beyond this phase, once we succeed, let's suppose we succeed and we do all our best in order to be sure we are online with this expectation, we will need clearly to have a capacity to demonstrate that it is a good investment to move on with this technology, knowing the potential advantage of it. So my conviction is clearly in a world where people are requesting safety, are requesting, okay, no impact on environment, no impact on the climate, and clearly also competitive cost, okay, the fusion technology could be really an attractive option for the investors. So it is on this way we are working. I am pleased to say that since I am in office, I saw a continuous increasing interest for fusion. We always, for example, in the very recent years, saw new small company moving on fusion to try to bring some added value to the potential which the fusion are representing, and we are, I believe, in the good trends in order to fulfill the expectation of the consumers as well as the investors.
Thank you very much. Rory, you're last to answer this question.
So after 5 speakers there, is the message clear? We need cash. I think that's pretty consistent. When I first joined the organization at its conception about 4 years ago, I thought very wrongly that the biggest challenge would be developing the technology. It has not been the biggest challenge. The biggest challenge has been raising finance. But as Simon said earlier, the numbers are not huge. The numbers for these large industrial investors, we're talking about $1 billion plus or minus to build the first commercial demonstration plant. And the rewards are very large. Fortunately, we've been successful up to now. All of our financing has been from private investors. Generally, it's been from multiple small angel investors and small private equity firms. They've done very well. In the past year alone, they've made a 6-fold return. And we're expecting that to grow even further. Right now, we are looking for corporate investors to really bring this up and allow us to move much faster. We expect the returns for them to be even greater, of course. The funding announcement from the UK government for us that's announced today, we expect that to leverage many times more from the private industry. So we're looking forward to reaching out there.
Thank you very much, gentlemen. We have come to the last question, the 5th question. This is going to be by David Desmond from Atom.
In the past years, nuclear projects have had difficulties in procuring and manufacturing what was designed, leading to rework, change of design in the course of projects, delays and overcost. One key lesson is that we have to involve the supply chain at a very early phase of the design. So my question is, how far do you involve the supply chain in your projects, and how do you see the strengthening of this involvement in the projects to come?
Troels, this time you start. Supply chain.
Yes. Yes, actually, we are here, right? There's a reason for this. I don't expect investor money. I said that from this crowd. So we're actually here to engage with the supply chain. And when I say the nuclear industry will crumble here in Europe, there will be an industry in the world. Nuclear will be revived. And, of course, there will be a lot of companies in that supply chain. We are at an early stage. We engage with the supply chain, and I don't have a lot to say here because we are so early that engagement with the supply chain also demands the supply chain to actually engage back. And it's hard at this stage. Everybody wants to make money, and making money on the flip side of 2025 is hard for small companies, and that will be the main supply chain.
Okay. Simon, please.
This raises a couple of good points. Just back to cost. I mean, we believe we can achieve our cost proposition with a very different technology choice, but we've also got a small modular reactor. We're designing a modular system, and when you have a modular system, you need to incorporate early modularity up into your supply chain, and that is important if you are to secure the benefits of modularity and the benefits of scale production. We recognize that the supply chain is, as I said, it's a supply chain that's 50 years old in a mature industry, and they're capable of early on contributing to certain risk elements in our project, namely demonstrating and ensuring the constructibility of the power plant and demonstrating the manufacturability of the components. So we are engaging with our supply chain. We are actually in the point in our engineering now that we can actually formally reach out to our supply chain. We'll be expecting to make a number of procurement announcements over the next 6 months.
Okay, Jeff, please.
Okay, needless to say, supply chain is absolutely critical. We use them and we involve them as much as possible in our design process. And basically to ground our process in reality. We look at feedback from supply chain involvement on cost estimates for systems and components. We also look at supply chain to assist us in maintenance, ease of maintenance of our systems. And we also look at them to help us with innovation in terms of designing our systems. For example, we had a situation where we might have eliminated welding from our core barrel based on feedback from supply chain. So, I mean, we work with a number of partners, strategic partners, that actually believe in our project quite a bit because they contribute financially to what we're doing. I mentioned a company, Burns & McDonnell, EPC, SGL for graphite, Centris for fuel, Curtiss-Wright. We work with them, pumps, motors, valves. So it's very, very comforting to get that vote of confidence from them, taking the long-term view. The other thing is we're looking at innovation in supply chain, how to engage a supply chain that's not actually involved in nuclear right now. So there's an organization called AMMI out of the U.S. that actually is working with non-nuclear suppliers and actually helping them along in terms of their quality assurance programs, et cetera, and making them sort of nuclear-ready suppliers when we need them. So I think as our design matures and we're ready for them, we will actually engage this innovation that's currently happening.
Thank you very much. CEA, Monsieur Gauché.
Yes, thank you. So the issue of involving the supply chain was taken very seriously into account and very early in the Astrid project. Since 2010, basically, we asked our industrial partners, and we have collaborations with them, to look not only at the design studies, but also to, let's say, more or less commit or at least launch all necessary R&D actions or qualification actions so that the manufacturability of what they were proposing was granted and not pushed to move to a later stage of the project. And this is why we have several partners like CNIM and Mitsubishi Heavy Industry, Framatome. They look at the manufacturability of large mechanical components, the core support structure, upper core structure, reactor, slab, heat exchanger, and so on. But we have also Bouygues for civil works, because we think we can be also very innovative with regard to the way concrete is poured, basically using mixed steel concrete structures, for instance. We have also Alsan for tubes for fuel sub-assemblies and all these kind of things with Technetics for the sealing of the reactor slab, Velan for some large diameter valves, General Electric on the gas energy conversion system, and Orano, of course, for the manufacture of fuel pellets. We think we can have savings in involving these companies, not only to look at the manufacturability, but also to make innovations in the way they will fabricate things in the future. And we think that sometimes innovation is hidden in the detail. And of course, we also try to use through this set of partners that are not only involved in nuclear industry, but have also other sectors of activity to integrate into our design new ideas where, let's say, there is more built elsewhere than in the nuclear industry. Thank you very much.
Monsieur Bigot for ITER.
As you know, we are now in the phase of manufacturing. And so what I could say is that we need to work very tightly with our supply chain, with our suppliers. It is absolutely needed because the performance we required from them are very, very challenging, and we need to work absolutely together. It is during the design, and we have developed some co-design with them, taking full advantage of the knowledge of the feasibility, of the constructibility of our component. And also during all the quality process, we work very tightly with them. Now we are moving in the installation. And again, we work very closely with the supply chain. We, for example, set up what we call the holistic integration team, which means that we will gather in the same team not only our engineer, but also the engineers of the contractors in order to optimize the sequence of the different installation step and maybe adjusting some of the design in order to be sure that we have a global overall optimization. So for us, it's absolutely critical to have suppliers fully embark with us. Some of the components which has to be manufactured, they last for more than 4 years. For example, the vacuum vessel sectors, these 9 different sectors which will contribute to manufacture the vacuum vessel sectors, the best company in the world, working sometime 2 shifts, it will last 4 years. So you understand that it is a long joint journey with the suppliers in order to be able to fulfill the expectation. And I am pretty sure that in the future, we need to keep on this way to proceed.
Thank you. Rory.
Thank you. We're actually taking a bit of a different approach with our suppliers, as in manufacturers of components for the reactors. We're being a little bit more conservative. In the UK, with the recent new build program, there was big promises made to the supply chain that the industry is going to grow very fast, there's going to be huge opportunities, and they got on board. And actually now a lot of them have pulled out because the projects have been delayed. So we're cautious not to overcommit to the supply chain. However, for engineering service providers, that's a bit different. We've relied quite heavily on them to increase our skills and our capabilities. It increases credibility quite substantially. For example, the roadmap I mentioned earlier was done with AMEC Foster Wheeler, now roadmap. Our costings were done by Atkins independently. And that model we would look to grow. We're currently looking for an engineering service provider, partner, so a strategic partner that can assist us with the engineering needs we have over the coming future. We're not just looking to pay them the normal rates because there's such a big variety. We're looking for someone that can bring the right skills but also share the risk and the benefit moving forward. And the model there is really so that we'd stay small and nimble. We don't want to be the 100+ organization that some of the other vendors are out there. We want to stay as small as possible and lean on the engineering partners to grow moving forward.
Thank you, Rory. And finally, Mr. Pershukov.
Okay. For us, it's not question. For us, it's life. Why? Because Rosatom has the largest nuclear power plants construction portfolio, including research reactor and supply of fuel and services. This portfolio for the next 10 years exceeds $130 billion. How to do it? How to realize? How to construct? For us, it's a very, very simple answer. We need to find our partners in the location where we construct new NPP and arrange the localization. Localization will manufacture some part of equipment and construct that. And we're doing. So without localization, it's also the requirement of some countries and some owners of future NPP, the project is not exist, it's not happened. And so for us, it's not the question, it's a real life. And regarding the generation 4, some different story, because we need to distribute our IP, and we need to find some suppliers that are producing typical equipment without some know-how, or we need to open our information. It's one question. The second question, that for all new suppliers, for new reactors for Gen 4, we need to have some research infrastructure, because they need testing for irradiation, testing for new materials, testing new fuels, and other. How to construct, how to use, and exist or not exist this research infrastructure where we can test our suppliers and our partners for future reactors. Unfortunately, no. Now we have just one reactor, Bor 60, in the world that operates on the fast spectrum. In the 2030, in the world, we will have just 2 reactors, high energy. It's Zholgorovets and Mir, both under construction. And so, need cooperate with suppliers, need cooperate for between a few partners who create the research infrastructure and propose for the world suppliers some possibility for testing new equipment, testing new materials, and other. For that, we need to arrange the cooperation. Now we are working with everybody. We create the consortium for initial stage from BIR. I know this type of consortium created Zholgorovets for all suppliers. We use a scheme of ITER project because we participate in ITER project very, very close. And so we really understand the ITER project demonstrate as best quality management to arrange the cooperation of existing producer and future producer of type of technology and equipment just now. And so, again, it's not the question, it's our life.
Gentlemen, you respected perfectly the timing. It was not an easy task. I think you are ready now to enter the political debate, and our political leaders have to watch out for you now. So, gentlemen from the audience, I think they deserve a big applause. I have two announcements to make before you leave the room. The first one is that we are going to meet again at the Workshop 2 lounge. Our charming ladies, our charming hostesses can lead you there if you want to have private questions with our speakers. There they will have something to eat, but we have time to discuss a little bit. The second announcement I have to make is that in October, actually at the 16th to 17th October, there will be a Generation 4 International Forum Symposium here in Paris again. Are you lucky? You can come back in France. So there are some leaflets outside. If you are interested, you can take them. See you at the Workshop 2 lounge, and thank you very much for having been with us.